We looked at limits in an earlier video, which is linked in the description. The Dirichlet function is a strange function that is discontinuous everywhere. As we will see, this means that it has no limits anywhere. This behaviour means it is often referred to as a pathological function when we are looking at limits. This video is part of a series on calculus, and I also have a calculus book available. See the links in the description below. The Dirichlet function is a piecewise function. It has a value of 1 if x is rational, and 0 if x is irrational. The stylized letter q represents the set of rational numbers, so the function is 1 if x is a member of q, and 0 if it is not. It is sometimes also called the rational indicator function, written as 1 subscript q, because its value indicates whether x is rational. Despite its appearance, this is a function, not a numerical expression. To fully understand the Dirichlet function, we have to recap a few facts about real numbers. We can represent the set of real numbers as a line, stretching from negative infinity to infinity. Every point on the line represents a real number. Every real number is either rational or irrational. A rational number can be expressed as a ratio of two integers. An irrational number cannot be expressed as a ratio of two integers. Famous examples of irrational numbers are the square root of 2 and the constant pi, but of course there are infinitely many irrational numbers. Every integer n is a rational number because it is equal to n divided by 1, so 0 and 1 are rational numbers, and we can mark them on our number line. The halfway point between any two integers is also a rational number. For example, 1/2 is a rational number, and so is 3/2. The halfway point between each of these numbers is also rational. There are quarters, for example 1/4, 3/4, 5/4, etc. We can create further rational numbers based on eighths, sixteenths, and so on. Every step generates more rational numbers that are even closer together and more densely packed. In fact, if we choose any two values a and b on the real number line, there will always be a rational number between them. We can go further and say that there will be infinitely many rational numbers between a and b, no matter how close together a and b are. And so far we have only looked at a small subset of the rational numbers that take the form n divided by a power of 2. It doesn't include numbers with a factor of 3 or 5 or 7 in their denominator, for example. So there are even more rational numbers than the ones described so far. What about irrational numbers? We know of course that the square root of 2 is an irrational number, because its exact value cannot be expressed as a fraction. It is also true that if we multiply an irrational number by a rational number, we get another irrational number. So root 2 divided by 2, that is root 2 multiplied by 1/2, is irrational. Similarly, root 2 over 4, root 2 times 3 over 4, and root 2 times 5 over 4 are all distinct irrational numbers. So are the multiples of root 2 over 8. So again, if we choose any two numbers a and b, there will always be an infinite number of irrational numbers between them. And again, we have only considered irrational numbers that are multiples of root 2 divided by a power of 2. There are even more irrational numbers that we haven't considered. For example, a rational multiple of root 2 with a factor of 3 or 5 or 7 in its denominator. There are also infinitely many sets based on other irrational bases, for example fractions of pi. To summarise, if we choose any two numbers a and b, no matter how close together, there will be infinitely many rational numbers between them, and infinitely many irrational numbers between them. Since we want to show that the Dirichlet function has no limit anywhere, we need to be clear what that means. We will use a simple definition of a limit. The full definition is presented in the video mentioned earlier. The reasoning presented here works with that definition too. We say that the function f of x has a limit L as x approaches a, if f of x is close to L whenever x is close to a. More precisely, if x is anywhere between a minus delta and a plus delta, then f of x will be somewhere between L minus epsilon and L plus epsilon, where delta and epsilon are both very small numbers. Furthermore, we can make epsilon as small as we like simply by choosing a small enough value of delta. And the opposite is true. If we can't make epsilon very small by choosing a very small value of delta, then f of x has no limit as x approaches a. We know that for any number x, the Dirichlet function will have a value of 0 or 1. and never any value in between. It follows therefore that whenever the function value changes between 0 and 1, there must be a discontinuity. It can't be a gradual change because that would require the function to take intermediate values between 0 and 1, which it cannot do. We can show this function as two dashed lines, y equals 0 and y equals 1. This represents the fact that the function continuously switches between 0 and 1 without ever taking any other value. We also know that for any two numbers a and b, however close together they are, the interval between them will contain both rational and irrational numbers. This means that the interval between any 2 points must contain a discontinuity. Since no 2 points are connected without a discontinuity, we say that the function is discontinuous everywhere. Let's pick some number a, for example we will choose 2, and then some value delta, for example 1. The interval between a minus delta and a plus delta is shown here. There will be both rational and irrational numbers in this interval, so the function will take values of 0 and 1 at different points between a and b. Now let's make delta smaller. Everything we have just said remains true. The interval between plus or minus delta of a will still contain points where f of x is 0 and points where f of x is 1. This will be true no matter how small we make delta, and no matter what value we choose for a. For a limit to exist, there must be some region where f of x is always close to some value L. But within any region, the function will always change between 0 and 1, so there can be no limit anywhere. If you enjoyed this video, please like and subscribe. You can also join my Substack newsletter. This video is part of a series covering calculus. I also have a book to accompany these videos. The links are in the description below.